Hello everyone, this video is for Aerospace Engineering, Activity 3.2.4, Orbit Types. So the main lesson objectives. At the end of this lesson, students will know or be able to do the following. Identify the various types of satellite orbits and the advantages and disadvantages of various orbits. So special orbit types. The Keplerian element set chosen for any given satellite is highly dependent on its mission. So certain orbits are better suited for certain missions. So you'll see going forward that there's some orbits that are very extreme, but they do serve a specific purpose. So the first one is a low Earth orbit. So there's no specified minimum altitude as far as what constitutes a low Earth orbit. We'll talk a little bit more about that here in a second. But it is relatively close to the Earth, so we're talking several hundred kilometers. And it has a short orbital period of about 90 minutes, so it can, make its way around the planet in 90 minutes. And so you can have many revolutions around Earth during a 24-hour period. Has limited swath areas, though, since it's kind of really pretty close to the Earth. You're not going to get a lot of inclination. But what can the satellite view from the Earth's surface? And then all manned space missions except lunar missions or LEO missions. And a lot of the Earth observing satellites are weather and imagery, so it's pretty close to the planet, so we can see that weather and we can see more details of the topography. And so let's kind of talk about why that is. So you can see here that we've got a representation of the International Space Station, and so you can see that it is pretty close. Even though we think it's way up in space, it's still pretty close to the planet as it kind of orbits around. So this image is to scale, showing that the height of the orbit is about 350 kilometers. So we also have a geostationary orbit as well. And so this is where the satellite remains over one location on Earth, and where its period is exactly 1 day. So you can see that as this orbits around, it's actually maintaining the same position, it's focused on the same spot on the planet as it kind of goes around in its orbit there. So usually the altitude for this is pretty far, so 22,200 miles or 36,000 kilometers. And its inclination is exactly 0 degrees, so it's lined up with the equator. Geosatellite only exists directly above the equator, and a geostationary satellite can see 70 degrees north and south of the equator, so you get a little bit more view range out of it from that distance that's really kind of out there. Geostationary satellites are mainly used for communications or permanent relay station in space. So again, it's kind of like connected to one spot on the globe, so it makes it a lot easier to do those types of things. Only one altitude with a period of 24 hours. So again, it's kind of maintaining the rotation of the Earth. And then all geostationary orbits are in a ring around the Earth too, so you can see that's kind of represented here, all the different satellites that are around the planet. And so we call this the geostationary belt. And it's a limited resource. We can only have so many satellites within this belt. And so sometimes a satellite is only going to last so long, and so we call that a geobird. And so when it actually is done with its service, it must be removed from its slot in the geobelt and must make room for another satellite, and it's usually boosted to a slightly higher orbit. So they may somehow get it so that it has more velocity to escape that orbit, and then it will just continue to drift out, or they'll just leave it and they'll just kind of let it continue to fall out so that something else can take its place. It's difficult to orbit exactly a 24-hour period with a 0 inclination, and orbits typically have some inclination, so they might be a few degrees above or below the equator, so we can't have it perfect. And then satellites drift slightly north or south of the equator, or slightly east or west, just because we don't have a perfect period. But small orbit adjustments small orbit adjustments are performed with a slight burn, so they'll, provide some type of a rocket boost just a little bit to kind of keep it in its orbit. And satellites with a 24-hour period and a non-zero inclination are called geosynchronous. Geostationary and geosynchronous terms are kind of used interchangeably as well. So then we have the real GeoBelt, and so before we kind of saw the dots, but what are those dots doing? So you can see that here's the ground traces from the satellite itself. So you may have somewhat of a ground trace going on here, but it still maintains that orbit. And then large inclinations run out of station keeping fuel, so it takes a little bit more to keep these satellites in its position. And sine wave orbits are being drifted into a new location as well, which you can kind of see right here. It does kind of manage to skip ahead a little bit. And then orbit color, participation in data sharing program, whatever that means, I don't know. We'll kind of skip this part here and we'll talk about this more in class. Another type of orbit is a MAHLI or a Molniya, and this uses a geostationary satellite for communications where there were parts of the globe that had a pretty high inclination. So here you can see that most of Russia is north of 70 degrees latitude. So how would you actually be able to take advantage of satellites orbiting the planet when you're located that far above the equator? And so they created this orbit called the MAHLI or the Molniya that would kind of help with those long-term communications over northern land masses. And so this is kind of what it looks like, where a satellite will go way out and then it'll drop way down. And you can kind of see when it actually does get a chance to capture some of those land masses there. So it's a highly inclined and highly elliptical orbit. The high inclination covers even northern Russia, but it also has a high eccentricity and a large apogee altitude as well. So you can see that it's really far out there. It's very slow at its apogee, so it's moving really slow, but then as it comes back down, it does speed up. If the apogee is over Russia, then the satellite hangs over Russia, so that's Kepler's second law that has to do with shape. And then this is what the ground trace looks like, and it looks different than a lot of other ones. It kind of even overlaps it a little bit, but it does have that hang time, which allows it to capture parts of those northern latitudes. We also have a polar orbit. And so this orbit is going to be 90 degrees to the equator. And so a satellite in a polar orbit will eventually pass over every part of the world. So this makes polar orbits well suited for satellites gathering information about the Earth, such as weather satellites. And a special type of polar orbit is called a sun-synchronous orbit, which passes over the same part of the Earth at roughly the same local time every day. And so, why would this be useful? Well, you could see changes in those areas as, you kind of go through time to see, what things are going on. And, that would give you important data that would allow you to maybe take some action. And then we also have constellations. And a single satellite is often insufficient to perform a particular mission. So we'll have a group of satellites in various orbits, and they work together to accomplish that mission. And so when we have a group of satellites working together, we call those constellations. And so GPS is an example of a constellation type orbit. Okay, that does it for this video. If you have any questions going forward, as always, be sure to ask.